So let's talk about independent events. You are probably familiar with determining whether events are independent or dependent. But we're going to go a step further in Algebra 2, and we are going to determine whether two events were independent based on their probabilities. Because sometimes looking at the events alone, it's hard to know. So we're going to go a little bit deeper there. Let's start to review with the definition here. When the occurrence of one event has no effect on the occurrence of another event, those two events are called independent events. We have some examples below. Determine whether each of the following events are independent or dependent. The first one, tossing a coin twice and getting tails each time. Tossing the coin has no effect on that next flip, so those are independent events. Second one, draw a king from a shuffled deck and put the card back. That's important. Reshuffle the deck and draw a queen. Now, because I put the card back, I did not change the sample space. Nothing happened. So this is another independent example. The third one, draw an ace from the shuffled deck, but keep the card out, reshuffle the deck, and draw an ace. Now, this has now become dependent because I've taken a card away and there's one less opportunity to draw that card. So this is now dependent. I've changed that sample space. There's been an effect on our next event. Last one, drawing a number cube twice and getting an odd number on the first roll, even number on the second roll. Nothing has changed here between the first roll and the second roll. There is still equal chances to roll a number. So these are independent events. So let's look at how we would find probabilities of independent and dependent events. If the two events are independent and you wanted to find the probability of A and B happening together, kind of like the examples above, we wanted to get a tails and a tails of those two flips of the coin, then you are going to multiply your two probabilities together. So whenever you see and, I want this and this to happen, means you need to multiply your probabilities together. If the two events are dependent, like when I drew cards from the deck, but then I put them to the side and then went back to draw some more, then you're still going to multiply. You're still finding the probability of A and B happening. You're still going to multiply, but you are going to find your probability of B after A has already occurred. So that conditional probability that we were just talking about. So whether it's removing a card or putting marbles out to the side or whatever, you want to make sure that your second probability is calculated after the first has already occurred. We've got some examples here below. Let's look at them. Number one, the red number cube and blue number cube are rolled. What is the probability that a blue 5 and a red even are rolled? So probability of a blue 5 and I want a red even. So the probability of rolling a 5 on the blue number cube, there's only one 5 out of 6 sides of this number cube. And I want something else to occur together, so I'm going to multiply that with the probability of rolling an even on that red number cube. There are 2, 4, and 6, 3 options out of the 6 sides. Multiplying these together, we get 3 over 36, or simplify to 1/12. Now, these were completely independent events. The blue number cube, the red number cube are not going to influence each other, so I just multiplied those probabilities together, 1/12. Number 2, a card is drawn from the deck of 10 cards numbered 1 through 10, and the number cube is rolled. So we got decks of cards, we got a number cube, completely independent events. Probability, find the probability that a 10 is drawn and a 3 is rolled. Draw a 10 and roll a 3. All right, so what's the probability of drawing a 10 out of that deck of cards numbered 1 through 10? There is 1, 10 out of the 10 cards. And so I'm going to multiply my probabilities together. Rolling a 3, there's 1, 3 out of those 6 sides. Multiplying across, I got 1 over 60. Our next example is there are 4 green, 6 red, and 5 yellow pencils in a bag. One pencil is selected and not replaced. It's not put back in. So I selected a pencil, I gave it to a student. If I go and select another, I guess I'm going to hand it to another student. So we are losing pencils as we go. You see that? Number 3, find the probability that a yellow and a red pencil are selected. Probability of yellow and a red. Okay, what's the probability of a yellow? There were 5 out of our total number of 15 pencils. And I also want to draw a red. Now I took that yellow and I handed it away. It's gone. It said in the description that we are not replacing them back into the pile of pencils. So to go and draw a red, there are 6 red, but now there's only 14 pencils in the jar, in the bucket, in whatever. So let's multiply these. I'm going to reduce these so these are a lot easier for me. I'm going to change 5/15 to 1/3, 6/14 to 3/7, and this is a lot easier for me to multiply. 1/7. The probability of drawing a yellow and a red without replacing it, 1/7. Number 4, find the probability of 2 yellow pencils. So a yellow and another yellow. I want both of those to occur. Yellow, there was 5 out of the 15, and means I need to multiply my probabilities together. Now I took out a yellow, I'm holding it. I'm not putting it back in there because I need 2 pencils. So now there are 4 yellows out of 14 total. So I'm going to use the same process to multiply these really quick. 1/3 times 2/7 will give me 2/21. Number 5, find the probability that 2 green pencils are selected. So a green and a green. All right, how many green did we have? 4 out of 15 total. And multiply your probabilities together. Another green. Now there's 1 less green, right? 3 out of 1 less total pencil, 14. On this one, I'm going to multiply these really quickly by reducing down to 2/7 across and 1/5 across the other way so that I have 2/35. All right, so here's where we're getting focused in for Algebra 2 is sometimes it may not be obvious whether 2 events are independent. So we can use the probabilities, like our values for our probabilities, to help us determine the independence. There are 2 methods for determining whether the events are independent. So method 1 is to test whether the probability of A and B is equal to the probability of A times B. So if you compute those and they are the same, then events A and B are independent. The second method is to test whether the conditional probability of A given B is equal to the probability of just A. So again, you can compute both probabilities and see if they are the exact same value. And if they are, then event A and B are independent. Notice in the conditional, you're comparing the probability of A given B to just the probability of A. So let's look at number 6. We've got a group of students at a high school took a standardized test. The number of students who passed or failed the exam is broken down by gender in the following table. Determine whether the gender and passing the test are independent by filling in the blanks in the sentence below, rounding all probabilities to the nearest thousandths. So we've been given a table, again, helpful to have our totals. So let's go over here and total up all of our columns and rows. We've got 125 passed total, 102 failed total, 158 males, 69 females, and our grand total is 227. Those are just always really nice to have off to the side as we fill this out. Now, number 6 and number 7 on our notes here are directly from Delta Math, and they are different. Look at how they are setting up the problem. They've said since the probability of female times the probability of fail. So they are getting us prepared to compare this first method. We're going to see if the probability of A and B is equal to the probability of A times B. So we're doing kind of that second part first. So I need to find the probability of females, and then I'm going to multiply it with the probability of fail. So probability of females, there is a total of 69 females out of grand total 227. That's my probability of female. I'm going to multiply it with probability of fail. We had a total fail 102 out of 227. Multiplying those together and rounding to that thousandths place is 0.137. Okay, so you would do that scratch work on your own, and in your box on Delta Math, you would plug in that first probability, then continue on the probability of female and male. This is that first part of method 1. So I want to find the probability of female and fail. Going up to my table here, that's the 65 out of your total 227. That probability rounded to the nearest thousandths is 286 thousandths. Now, because these two results are unequal, that means that these two events are dependent. We literally got two different values here. We got 137 thousandths and we got 286 thousandths. Not the same, so therefore they are not independent, they are dependent events. Let's do it again. Number 7, the group of students at the high school took the standardized test. The number of students who passed and failed is in, and gender is in our table. Determine whether gender and passing are independent by filling in the blanks. Again, it's really nice to have our totals, so let's add these up. We have 84 that passed, 21 that failed, a total of 40 males and 65 females. Our grand total is 105. So this time, look how Delta Math is setting up this question. We're looking at the probability of female given that they passed. So looking at only my passed column, 84, of those that are female, 52. So 52 out of 84, rounded to the nearest thousandths is 619 thousandths. And we're going to compare that with the probability of female out of everybody. So total female was 84 out of the total class 105. Rounding that to the nearest thousandths is also 619 thousandths. So the two results are equal, and therefore the events are independent. Before we move on, I do want to add to this video that I do feel like this scenario for these problems is really inappropriate. I don't think passing and failing is independent or dependent on whether you are male or female. So this does bother me a lot. I have trouble with this lesson on Delta Math, and I think they need to change the scenario because there's no reason why male and female should be dependent on whether you pass or fail or vice versa. So number 8 through 12, we're doing what we've done in the past. We're going to take our probability formulas and compute various other values. So given that the events A and B are independent, they've already told us, hey, they're independent. You can use those independent rules at the top of our page. Probability of A is given, probability of B is given. Determine the value of B given A. So we're going to be using that formula from method 2. It says that if I have the probability of a conditional probability, B given A, now notice our letters are switched here. It needs to be equal to the probability of B. So if you want the probability of B given A and it's independent, it should be equal to the same value as probability of just B. So this is actually very straightforward. I don't need all the numbers that they gave us. If I want the probability of B given A, and those events are independent, then it's equal to B, the 74 hundredths. Done. Number 9, given that A and B are independent, so we can use those rules above with probability of A is given, probability of B is given, determine the value of A intersection B. Now you're looking above, right? And you're like, Ms. Bryan, where is the intersection? Intersection means the same as and. This means the same as and. So we're going to take the probability of A intersection B, and if they're independent, it means that I can take the probability of A and multiply it with the probability of B, and that would be the same value. So the probability of A intersection B, that probability of A was 36 hundredths. I'm going to multiply that with the probability of B, 7/10, and that gives us 252 thousandths. Number 10, given that the events A and B are independent with the probability of A given and the probability of A intersection B given, determine the value of probability of B rounding to the nearest thousandth if necessary. So we again are going to use that first method at the top. I know the probability of A intersection B, since they are independent, is going to be equal to the probability of A times the probability of B. Fill in what I know. I know this is 0.216. I know the probability of A is 3/10, but I am missing that probability of B that we're looking for. So we're just going to solve. Divide away the 0.3 on both sides. So your probability of B is equal to 0.72 or 72 hundredths. Number 11, given that A and B are independent, with probability of A is given, the probability of B given A is given. Determine the probability of B and round to the nearest thousand. So we're using that second method. They gave us a probability of B given A. If they're independent, it should be the same value as just B. So they said probability of B given A is 0.76. We are looking for probability of B. And guess what? I'm done. This one always seems to send me for a loop. Because I'm like looking to solve and plug in and I'm like, wait, where is that? Where is it going? It's right there. So your conditional probability is always equal to the probability of just that numerator. Last one, given that the events A and B are independent, with probability of A is given, probability of B is given, determine the value of A given B. Now, what did we just say? The conditional probability, if they are independent, is equal to just that probability of A. Am I already done? I think so. If I'm looking for the probability of A given B, they already told me that A was 66 hundredths. So we are done there. You can see from those last examples, there's tons of variation there. They can use the intersection symbol or use the word and. They can mix up and rearrange those conditional probabilities, the probability of A given B or the probability of B given A. So just watch out, take it slow. That is the context of our standard, also determining whether two events are independent given their probabilities. If they are equal, if you find that their probabilities are equal, then you are going to have independent events. If you find that they're unequal, dependent events. Practice that, guys, and I'll see you in class.